Today we're going to go over fan curves, how I read them, and how I use them to select fans. This is what a fan curve looks like, and there's a number of things going on here, but first just focus on this red line right here. This red line is the fan curve, and it represents the performance of the fan given a set of external circumstances. And when it comes to performance, the two key outputs we're looking for are the static pressure of the fan, or how much resistance is the fan able to overcome to move air, and the volume of air that it can move, so the overall CFM that this fan is able to move. And the static pressure and the CFM have an inverse correlation. So on the x-axis here, this represents the overall volume of air, and for this curve, this is per 1,000 CFM. And then on the y-axis, this represents the static pressure the fan is able to produce. Remember, this red line is what tells us how the fan will perform under certain conditions. So for this particular fan, if there is 0.4 inches of external static that it needs to overcome, this tells us that at 0.4 inches, this fan is able to produce right around 5,500 CFM of airflow, 5,600, somewhere around there. This is how we use this curve to determine the performance given a static pressure. We can look at it another way. If we need to move 5,000 CFM of air, then our static pressure cannot be greater than 1.2 inches. The higher the static pressure, or the more resistance in the system, the less airflow this fan is going to be able to move. So how do we use this in practice? As engineers, we don't start with a particular fan and then drive our design based on that. We do it the other way around. We determine what the system needs, and then we select a fan based on the system requirements. So let's say we've done our duct design and we've done our calculations, and we've determined that we need to distribute 5,000 CFM of air, and the ESP is equal to 1.2 inches of static pressure. These conditions right here that we calculated are what drive our system curve. These are our system requirements. So with these system requirements, we're going to start with 5,000 CFM, and we've determined that it requires 1.2 inches of static pressure to distribute all the way through the end of our duct run. Mapping that out, we're going to find where we fall on the fan curve. From there, we're able to determine properties of the fan. This is showing us that we intersect when the fan is operating at 1,289 RPMs. We can also use the fan's brake horsepower curve, which is this dotted line, to determine the operating horsepower at those conditions. And this kind of maps it for you, but to determine that, you would take that operating point, you would draw a straight line up until you intersect with the brake horsepower curve, and then at that intersection point, you are going to draw a line across to the secondary y-axis, and this is going to give you your brake horsepower for the fan. So about 1.85. So here, with this fan at this RPM and these conditions, the brake horsepower is going to be just over 1.8. Now, all these lines intersected really nicely because I used the Greenheck eCaps application to select a fan based on these system parameters. So it just gave me the RPM, and I have a nice intersection at my operating point. But with a generic fan curve, it's not necessarily going to look like this. Instead, with a generic fan curve, you might be looking at a family of RPM values and brake horsepower values. Most fans don't have just one operating point. They can be configured for different RPMs to accomplish different performance, and if they're direct drive with an ECM motor, they can actually vary the RPMs in real time to change what that fan curve looks like to better accommodate the system. Let's consider a different operating point. So say we need 4,000 CFM and our ESP is 0.8 inches. Now we'll plot that. Here's 4,000, here's 0.8. That puts us right here, which means for perfect alignment, our RPM would need to be at about 1,100 for this particular fan family. If that level of selection is not an option for this fan, then we're going to have to choose between one of these nominal operating modes. And if our driver is 4,000 CFM, then we're going to have to go up to our 1,200 RPM operating condition. And what this tells us is we have a little bit of extra oomph in the fan. At 4,000 CFM, we're able to generate over 1.2 inches of static with this fan, which is more than what we need. To balance the system to maintain this CFM for this fan, you may need to artificially increase your external static by slightly closing dampers and keeping this nice and happy. Another way to look at it is if the system is at 0.8 inches of static, then this fan is going to be able to generate more than 4,000 CFM. It's going to want to move closer to 4,500 CFM. This is why having variable frequency drives or ECM motors makes the system balancing process a lot easier, because you have way more control over the operation of this fan, and you're able to fluctuate and maintain optimal efficiency for the fan rather than oversupplying or overpressurizing and running at a non-optimal condition. Lastly, let's talk about this gray area over here. This is the do not operate area. Fans have an operating condition where they will start to stall if they're moving too little air. So as you decrease in CFM and get into this portion here, this is the danger zone where the fan may stall if it's not able to move enough air through it. When you're selecting a fan, you want it to be somewhere within this region of the curve. This gives you enough buffer on both sides for when your system changes. Remember, your system curve is not a static thing. It can change. If you're closing dampers, that's going to increase the static pressure. And as we saw at the beginning, if you increase the static pressure, you're going to decrease the CFM. So if your selection puts you right here on the fan curve, then increasing the static pressure is going to get you real close to that danger zone, which you want to avoid. On the flip side, if you select too close to the upper limit, you're never going to hit a point of zero resistance. That's not possible in a ducted system, but your fan will not be running as efficiently. The sweet spot for efficiency is typically right here within this range, so that's what you want to aim for. And most importantly, you want to avoid being too close to the danger zone up here.